Hello, quick video on correlation. We often have two variables and we want to know if they're related. We quite often draw a scatter diagram like I've got down here in the bottom left for that to have a look at that, and maybe draw a line of best fit. But it would be useful to have a measure. Well, Carl Pearson at UCL about 100 years ago created a measure called the correlation coefficient. Here's the formula for it. And this is a measure of the co-relationship between the two of them. Yeah, there are symbols we can see here that we can recognize. That's the sum of squares of our x values, and here it's the sum of squares of our y values. And at the top we've got a new idea, which is the cross product of the differences, and we'll work on what that is, how we get that in the next section. Okay, let's use an example. Let's look at the importance of scoring goals to winning football leagues. And we've got the Premier League data here for 2003. Just here we go. There's the data. So Team A here, which I think was Arsenal, won the league. They scored 73 goals and they earned 90 points. At the other end, I think it was Wolves, scored 38 goals and earned 33 points. Okay, well, the mean number of goals in the league was 50.6 and the mean number of points was 51.6. And we can compare the differences in for individual teams from those means. So let's have a quick look at teams and some figures for individual teams. So Team A, Arsenal, scored 22.4 goals more than the mean and earned 38.4 points more than the mean. Wolves at the bottom scored 12.6 goals less than the mean and earned 18.6 points less than the mean. And we can work this out for every single team. So here's a spreadsheet with the data in. Here's the goals. Let's start off with A there. There's our 22 goals plus. And there's our, in this row, here's all the goals for the teams. Here we go in that row, goal differences. And here's the points differences for each of the teams there. As you can see, the teams at the top end of the league, these figures are both positive, and at the bottom end of the league, both of these figures are negative, and that's what we'd expect if there's some sort of connection, a positive connection, i.e. more goals, more points. Okay, now what we're going to do is construct our SXX, which is our sum of the cross products, and to get that we get the difference in our x value for each team or data item. So here it's actual goals away from the mean, and we multiply it by our y, a distance deviation from the mean, which is our points scored for a team, and rather points earned from the mean number of points. And then we're going to sum the whole lot up. So quickly using as an example Team A, well, they scored 22.4 goals more than the mean and earned 38.4 points more than, so we multiply those together, we got 860 goal points for them. And the worst team in the league, they got minus 12.6 goals on compared to the mean and minus 18.6 points. So they ended up with plus 234 goal points. Note the signs are positive on both of those, because if we think about it, it's reinforcing the same point, isn't it? More goals equal more points and less goals equal less points. Those two are consistent. And if we add up each of those values, we're going to get our figure here of 2266 goal points. So looking on our spreadsheet here, here's our row of the values there, and as you can see, nearly all of these values are positive, aren't they? Even at either end, there's a bit of a couple of negative ones here in the middle, but pretty well they're all positive, which suggests there is some connection between goals scored and points earned. And if we add them all up, we get 2266. There's our 2266. But that's in goal points, isn't it? And that would suggest that if in the league people started scoring more goals, or if they arbitrarily changed the point scoring system, that number would get bigger. And what we want is something that's more standardized and isn't going to just grow to a very large number. And we do that by trying basically to work in standard deviations, yeah, as we've done in some other cases. And to do this, we're going to use our sum of squares. So here's our sum of squares for the x and our sum of squares for the y. And if we go into calculate those, we'll get these two values here. So let's have a look. Here's our sum of squares of the x values. There we go in that row, summing up to 1400, and our sum of squares in the y in this row here, summing up to 4300. Yeah. And this number here is in goals, and this is squared, and this number here is in points squared. So we need to get them down to just being goal points, so we're going to square root them. So that's why we're square rooting in the formula, so that we end up with a non-dimensional answer. Okay, so in this football example, our sum of the cross product sum was 2268 goal points, and on the bottom we had our two sums of squares, 1400 and 4300, square rooting those to get them into goal points. We end up with this number 0.886. So what does that mean? Well, in these in correlation, that figure, the math says it could only be between -1 and +1. And let's just have a quick look here. If we've graphed it, we can see here, there's our scatter diagram. We can see that there is a positive correlation between the two. Look, we've got a line going up here, haven't we? So I didn't draw that particularly well, but that's what we're looking at, isn't it? A straight line between the two, yeah. If we did that with a line of best fit by eye. So that means that there's a positive, isn't it? If we increase the number of goals scored, we increase the number of points. So we expect to see it being positive, our correlation coefficient. And the second part is it's quite a narrow little distribution here, isn't it? They're quite narrow. There's only a few outliers here, but quite a few of them are quite close to the line, aren't they? So if we had a look at that, yeah, ignoring these outliers, pretty well everything is pretty well on the line. That's what's giving us a big positive number, a number close to 1. So what we're saying here is we've got strong positive correlation between goals scored and points earned. Okay, and we can use our calculator to do this for us, our stats calculator. So let's go back here and have a look. Okay, what we've got here is lists of data. In the first list, we've put our goals, because in logically in the world, isn't it, the number of goals scored is driving the number of points. It's not the other way around. It's not the number of points driving the goals, is it? It's goals driving points. So we're going to put our goals in list 1, and then we're going to put our points in list 2, and we're going to work on two variable approach in our calculator. So we put those in. First way of having a look at the data is to just go in and have a look at the graph. Here we go with the graph. And here we've got our scatter diagram, just like the one we've got here from our spreadsheet. And the next thing we can do is head on and do a calculation. And here we're going to say we're going to look at x versus y. There we go. And our linear regression, that we'll come back to the wording in the next video, is the data correlating the two, and our value r here is in the third row down here, third row down, 0.8886. So there we are. That's what we were looking for. We can get it straight out of our calculator. Okay, let's do a bit of interpretation now on what's going on and what these signs mean. Okay, excuse me, just going to move it up slightly. So we've got the graphs in the picture. There we go, one more. All right, so our range we've said is between -1 and 1. The sign of the correlation coefficient tells us whether the relationship is increasing or decreasing, and the value tells us how strongly the correlation is. So let's have a look at some extreme examples. If I plotted all the points on our graph, our red points here, and as our x value increased, our y value increased, and they were on a perfect straight line, we would get perfect positive correlation, and we'd have an R value of 1. If I plotted points here designed to be on a straight line, that as the x value increased, the y value reduced, we would get an R value of -1, and that would be a perfect negative correlation. If I just plotted a jumble of points with no correlation here, I would get an R value of 0 coming out of my calculator. Okay, and if I wanted to look at the strength of the relationship, let's have a look at these. We'd be looking at the value here. So looking at our right hand diagram here, if we had little or no correlation, they would just be scattered around, and the best thing to do would be to draw a circle around them. And if we did that, our R value, our correlation coefficient, would probably be somewhere between -0.2 and +0.2, but very low or none. But if we saw that if we mark our points and then we can draw a sausage around them, that shows us that we've got reasonably strong correlation. We probably got values of 0.5 to 0.7. In the example we had earlier, where it was eating very narrow sausage, we were able to get a much higher value, and we were nearly at 1, weren't we, at 0.9 in effect. So the width of your sausage is going to tell you how strongly correlated they are. Okay. So here's a quick summary of this topic. Correlation coefficient. Our correlation coefficient measures how well two variables are related. Here's the formula for it, and we can get that out of our calculator. The usually called notation for it is R if it's a statistic, that is if we've just calculated it for some data. But if we were using it as a parameter in a distribution, we'd call it rho, a bit like we would, for mu for the mean of a population and x bar for its the value of a statistic. The range is of the R is between -1 and +1. It's positive if we've got a positive relationship between the two, i.e. as 1 increases, x increases, y increases, and it's negative if it's a negative relationship, i.e. as x increases, y decreases. And the value would tell us the strength. So if we've got a high number, we've got strong correlation. Weak, we've got a low number. And if we've got almost 0, we've got no correlation at all. So I hope that's of use.